Okay, so I'm going to fast forward to the part where we were at last time. We were talking about, again, Ørsted's law. And just to remember that Ørsted did this experiment where he was just generating electrical current. And then suddenly he had a compass near, and he noticed that the compass started moving when there was an electrical current. And that made him think, electrical currents then generate magnetic fields. So wherever there is, whenever there and wherever there are charges moving, we're going to have a magnetic field. And remember that charges moving is electrical current. So whenever that happens, we're going to have a magnetic field. So well, I'm going to leave it running so we can kind of remember this.
Starts to move when he turns the current off. Then he runs the current in the wire in the opposite direction. He sees the needle move the other way. What Ørsted demonstrated that day was a fundamental discovery, the connection between electricity and magnetism. And it changed the field of physics forever. The relationship. So
another thing there that's important is that, again, movement of charges generates magnetic fields. But the way that magnetic field is created depends on how the movement is done. So if the movement is going from A to B, we're going to have a certain type of reaction. If it's moving from B to A, it's going to be different. So the direction of the movement also affects the magnetic field. That could be a question in the next exam. Explain Ørsted's, what did Ørsted do, or explain Ørsted's experiment? Very simple. Like I mentioned, Ørsted was doing an experiment where he was creating an electrical circuit, and he noticed that when electrical current flowed through a conductor, a magnet that was close to the experiment started moving. That means that electrical current generates magnetic fields. Okay.
From the beginning, please.
Okay. Remember, it's being recorded. You don't necessarily have to write it down word for word. Again, the experiment was that he was creating an electrical circuit demonstrating the flow of electrical current, and he had a magnet near. So when he turned on the circuit, or when the electrical current was flowing, he noticed that the magnet moved. If the current moved in the other direction, the magnet moved in the other direction, in the opposite direction. So this demonstrated that whenever there is electrical charge moving, or whenever there is movement of electrical charges, and movement of electrical charges is electrical current, there are going to be magnetic fields created. Okay, there's going to be a magnetic field that's created. That was basically Ørsted's contribution with his experiment.
Between electricity and magnetism not only explains what Ørsted and the students witnessed in 1820, it also possible much of the technology that's used today, from hydroelectric dams to your smartphone. It even explains why Earth's magnetic field is essentially keeping you from being cooked alive right now. And all you really need to understand the basics of magnetism and electricity is this. You're probably familiar with the basics of magnets already. They have a north and south pole. Two of the same pole will repel each other, while opposites attract. Only certain materials, especially those that contain iron, can be magnets. It depends on their molecular properties. And other metals, including cobalt, nickel, and iron, are attracted to magnets, even though they aren't magnets themselves, like the metal in your refrigerator door. And there's a magnetic field around Earth, which is why you can use a compass to figure out which way is north. The magnet in the compass aligns itself with the Earth's magnetic field. Just as we use electric field lines to represent the electric field created by charges, We can draw magnetic field lines to represent magnetic fields created by magnets. And as with electric fields, the more crowded the lines are, the stronger the magnetic field. The lines point from the North Pole to the South Pole, like how electric field lines point from the positive to the negative charge. But there's a key difference. You can have an electric field spreading outward from a single electric charge, but that can't happen with magnets because you can't isolate one magnetic pole.
Another question that I could ask, these are things that I want you guys to remember. Tell me the difference between an electrical field and a magnetic field. What would be a difference between an electrical field and a magnetic field? In the case of the electrical field, an electrical field can be generated by one charge. One charge, an electrical charge can radiate an electrical field. In the case of a magnetic field, we always need two poles, which is the north and the south. Okay, we can't generate a magnetic field with one thing. We always need two, and the fields go from north to south. They're flowing. Okay, that's a basic difference between an electric and a magnetic field. The electric field can be generated by one charge or many charges. The magnetic field at least needs two poles to be generated.
If you chop a bar magnet in half, you don't end up with one north magnet and one south magnet. You end up with two magnets, each with its own north pole and south pole. This means that the magnetic field lines surrounding a magnet always form closed loops. We measure magnetic fields using a unit called the Tesla, which is 1 Newton per ampere meter, and 1 Tesla is a very strong magnetic field. The fields from some of the strongest superconducting magnets in the world are only 10 Teslas. Now, when Ørsted was doing a demonstration on that fateful day in 1820, he was using a regular compass magnet, but when he brought the magnet close to a wire carrying a current, the magnetic field from the current exerted a force on the needle, moving it to point in a different direction. Ørsted had discovered one of the fundamental principles of electromagnetism. An electric current produces a magnetic field.
That's what we've been talking about. An electric current produces a magnetic field. And that's where the field of electromagnetism comes along. So remember that the learning module is called magnetism and electromagnetism. So magnetism occurs in nature with these materials that are naturally magnetic, okay? Like the ones we mentioned at the beginning. But we can create a magnetic field artificially using electricity, and that's where electromagnetism comes along, or the creation of magnetic fields by electrical currents. And by the way, remember you guys, all of the or most of the things we're seeing during this course apply from A to B and from B to A. So what does this say here on the screen? An electric current produces a magnetic field, right? But it also, we're going to see that it also works the other way around. A magnetic field can induce a current. So if I have a magnetic field, if I have a magnet, and I just put a wire close to the magnet, the wire is going to have an electrical current going through it. So these properties work from A to B and from B to A. An electrical current produces a magnetic field. A magnetic field can induce or produce an electrical current.
After a few more months of experimenting, Ørsted figured out that when a current runs through a wire, the magnetic field that it produces surrounds the wire. Expressed with field lines, the magnetic field would appear as circles with the wire at their center. If the current was coming straight towards you, the field lines would be pointing counterclockwise. And we use the vector B to represent the magnetic field. The magnitude of the vector is the strength of the magnetic field, and the direction of the vector is the field's direction. Now, there's an easy way to remember how the direction of the electric current and the direction of the magnetic field it produces relate to each other. It's called the first right-hand rule because there are actually 3 right-hand rules. Just take your right hand and point your thumb in the direction of the electric current. Now curl your fingers. The direction your fingers are curling, that's the way the magnetic field lines are pointing. And likewise, if you know the direction of the magnetic field lines, you can use the rule to figure out the direction of the current in the wire. It really comes in handy.
Want to stop it?
Use the rule to figure out the direction of the current in the wire. It really comes in the way the magnetic field lines are pointing.
Yeah, so this is one of those weird things where there has to be some grand design. So we're fitted with right hands. So somehow our right hand can be used to model, yeah, the rules of magnetism in a wire, which is really weird that applies, but actually that happens. If I have any wire and I know where the direction of the current is going, the direction of the current is going to be my thumb, my right thumb. And when I curl my hand, the curling of the hand, that's going to be the direction of the field in that wire. And that's the first right-hand rule. There's modifications of this rule. That's why there's another rule, but that's going to apply. So the direction of the current, the fingers are going to indicate how the magnetic field is being generated. So if you're left-handed, well,
And likewise, if you know the direction of the magnetic field lines, you can use the rule to figure out the direction of the current in the wire. It really comes in handy. Now, if a current running through a wire exerts a force on a magnet, you might expect the opposite to be true as well, that a magnet exerts a force on a current running through a wire. And it does, which is good because that's what's protecting us from harmful radiation from the sun right now. The direction of the force from a magnetic field on a current running through a wire will be perpendicular to both the magnetic field and the current.
So what does this mean? So what are we relating? So a current generates a magnetic field. But if I have another particle in that magnetic field, there's going to be a force. Similar to when we have an electrical field, if I have an electrical field with one charge and I put another charge there, the charge is going to react to the electrical field, either going towards it or away from it, depending on if it's attracting or repelling. The same thing happens with a magnetic field. If I have a magnetic field that's being generated, and I have a charge, but here's the thing, the charge has to be moving. So it's kind of like the Jurassic Park thing, where if you've got the Tyrannosaurus Rex in front of you, you don't move, it doesn't recognize you. Supposedly, I wouldn't apply that rule in reality. It's very similar here in the sense that if the charge isn't moving, there isn't a force. In magnetism, the key here is movement. So if I have a charge that's moving through a magnetic field, there's going to be a force exerted. So that's why kind of on the Earth, the magnetic field of the Earth is generating kind of like a sort of a barrier of the electromagnetic and heat radiation that's coming from the sun and other spatial bodies.
Brings us to the second right-hand rule. This one helps you keep track of 3 directions: the direction of the magnetic field, the current, and the force. Here's how to use the second right-hand rule. Point your arm in the direction of the current, then bend your fingers so they're perpendicular to your palm. This represents the direction of the magnetic field. Your thumb, which is perpendicular to your fingers, is the direction of the force on the wire. But what about the strength of that force? You can use your hands to figure this out too, but you'll have to use them to do math. Sorry. The magnitude of the strength of that force. You can use your hands to figure this out. The magnetic field.
So the second right-hand rule says that your fingers are going to be indicating the direction of the current, and so your hand, I'm sorry, your arm, the fingers are going to indicate the direction of the magnetic field, and if those are aligned somehow, the thumb is going to indicate where the force is going to be going. Okay, the thumb is going to be indicating the force. The force is always going to be generated perpendicular to the curve. Okay, it's always going to be in the perpendicular opposing direction.
Your thumb, which is perpendicular to your fingers, is the direction of the force on the wire. But what about the strength of that force? You can use your hands to figure this out too, but you'll have to use them to do math. Sorry. The magnitude of the force from a magnetic field on a wire is equal to ILB sine theta. This equation tells us that there are 4 factors that affect the magnitude of the force. First, there's the current in the wire. That's I. And the stronger it is, the stronger the force is. Second, there's the length of the wire running through the magnetic field. That's L. And the longer the wire is, the stronger the force is. Third, there's the magnetic field B. And the stronger B is, the stronger the force. Finally, the closer to perpendicular the current is with respect to the magnetic field's direction, the stronger the force is. That's where sine theta comes in.
So, again, quick question that could also be asked. What are the factors, if I have a wire what are the factors that are going to affect the force on the wire? If I have a wire and a magnetic field. So everything's going to be directly proportional. The larger the current, the larger the magnetic field, and the larger the length of the wire, then the stronger the force. Okay, so everything's going to be directly proportional. Remember when we were talking about capacitance. So what are the factors that affect the capacitance? Well, the surface area. The larger the surface area, the larger the capacitance. But the distance between the plates, that was inversely proportional. Okay. Same thing with the electrical field.
What was inversely?
No, I'm giving an example of the
It was
previous.
the larger the word, the stronger the force.
It's the formula here. It's the current, the length, and the magnetic field. The larger any of these three are, the larger the force. It's always going to be directly proportional.
Is it the larger the current, the larger the magnetic field, or the force?
The force.
No, the force.
The force. So we're talking about
But
the
in the
force.
first one.
So that you're the current, magnetic field, and length.
The current, magnetic field, and length. So current, magnetic field, and length. The larger any of those are, the larger the force is going to be. So it's always going to be directly proportional. Okay, stronger. It's always going to be directly proportional.
That's why they'll multiply.
That's why they're multiplying, correct? And the sign of the angle, that only means that the closer, remember the right-hand rule. So the arm is the direction of the current. The fingers are the magnetic field. The closer we are to 90 degrees, the larger it is. So the closer the current and the field are perpendicular, that's going to make it larger. If they're not perpendicular, then it's smaller. That's why we have the sign of theta. The sign of 90 degrees is 1. The sign of any angle that's less than 90 degrees is less than 1. Okay, so if they're perpendicular, it's going to be larger. And those would be the factors that are going to affect it. Assuming that I have a wire that has an electrical current going through it.
So the factor will be out of the.
The factor, all of them, and they're directly proportional. So if any of them increases, the force increases. And I was just making the analogy, that when we were talking about electrical fields, it was a bit different because we were talking about distance. And so remember that distance is inversely proportional when we were talking about electrical fields. Here, everything is going to be, it's going to be directly proportional.
Maximum value is 1 when theta is 90 degrees, so the current is perpendicular to the magnetic field lines. That's when the force will be strongest. Similarly, the minimum value of sine theta is 0 when theta is 0, so that means the current is parallel to the magnetic field lines, and in that case, there won't be any force on the wire at all. Now, all of this math can help us understand how we're being protected right now from solar radiation. The sun is constantly shooting radiation towards Earth in the form of charged particles. But luckily for us, Earth has a magnetic field. Currents are made up of moving electric charges, so it makes sense that a magnetic field would also exert a force on single electric charges that pass through it. And this is exactly what the Earth's magnetic field does to the charged particles coming from the sun. It deflects them, sending them spiraling away and protecting us from the worst of the radiation. Let's suppose you wanted to find the magnitude of the force of the magnetic field on a single charged particle from the sun. All you'd have to do is change the equation we use for the force on the current to account for the fact that we're talking about a single charge.
Before we go to that formula, it's like, I don't know if you've seen the typical sci-fi trope when somebody's writing a script for a sci-fi movie that, whatever happened moved the axis of the Earth. And if the axis of the Earth is moved, then everything's gonna, well, the science fiction behind that has to do with this. Yes, yes. You're really dramatic when I hope you never have to give bad news because you're like, you know what? No, I'm sorry about that. I didn't mean to be.
I just wanted to ask you about the right-hand rule.
Mhm.
Can you repeat where the directions are, like what they mean? The
For-
thumb, what does it mean?
Well, remember that there's two rules. In
The
the
first one.
first one, the thumb is indicating the direction the current is going in the wire. Okay? And the fingers indicate the direction of the magnetic field. Okay? So if this is a wire, you said, and the current is going up, then the current is going up, that means that the magnetic field is going like this.
Okay.
If the current is going down, that means that the magnetic field is going like this. So they're little circles that are going around them. That's the first right-hand rule. The second right-hand rule says that now we're assuming that we have a magnetic field. We have a wire, and we want to know where there's current going through it, and we want to know the force that's being exerted. So in this case, the hand is going to indicate the current, or your arm. The fingers always indicate the magnetic field. And your thumb is going to indicate the force.
But what are you grabbing there? A wire also?
No, the thing that's happening here is, let's say that we have this wire here. Let's say that the current is going from the bottom. Well, this isn't being recorded, by the way, but it's only the audio. The current is going from the bottom to the camera. It's a very silly example, but the current is going like this. And there's a magnetic field being generated. But the magnetic field is also going to generate a force. So this means that the current is going like this. And let's say that I have a magnetic field around here. Let's say that the magnetic field is going like this. There are lines of magnetic field going like that. I have a magnet here. I literally put a magnet here, and that magnet is sending magnetic lines over there. Okay, we're good up to that point. So the current is going up. That's my arm. This is the magnetic field. Where is my thumb pointing? My thumb is pointing that way. That means that there's a force that's pulling the wire this way. Okay, now let's assume that the current is still going upwards, but now the magnetic field is going from you to the wall. The magnetic field is now going like that. So now the force, the wire is going to be pulled that way. That's what the second hand rule means. If you have a wire with current and there's a magnetic field around it, there's going to be a force that's being active on it. Your thumb is going to indicate where that force is going. Okay. Now that, just going back to, that's why wires have to be really, really shielded, because any magnetic field around this is going to generate forces. Okay, and we don't want that. So going back to the example of the Earth, that's why in a lot of science fiction things is that whatever's happening is moving the axis of the Earth, and well, moving the axis would basically mean moving the magnetic field. And so if the magnetic field of the Earth is oriented in a way that's shielding us from the rays of the sun, if I move the magnetic field or the poles of the Earth, that shielding is going to be affected. So that's a typical thing in science fiction, that the mad scientist or whatever is moving the poles of the Earth. That means we're all going to die in 8 minutes. It's basically that the magnetic field of the Earth is shielding us from this external radiation. It's one of the many things that's shielding us from external radiation. Now, the last rule, the third right-hand rule has to do, in this example that I gave, we're talking about a current. So there's a lot of electrical charges going through. But now let's assume that instead of being a current, it's just one charge that's being bombarded through a magnetic field. Imagine a weird analogy, at least in my mind it works, but you're going to have to imagine it. Imagine that there's a river flowing, and then you suddenly toss a rock into a river that's flowing from one point to the other. If the river was stationary, and I threw it like that, then it would probably go pump, 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 and go forward. But if the river is moving and I throw it, the movement of the river is also going to make the bounce of the rock move towards that. It's kind of similar here. If I have a magnetic field and suddenly I launch a charge into the magnetic field, that movement of the charge and the magnetic field is going to generate a force. So instead of the charge going straight as it should be, the charge is going to be it's going to be moved in another direction. That's basically what's happening with the radiation of the sun. And so the original formula that we saw can be modified for that situation.
The equation for the force of a magnetic field on a current says that the strength of the force is equal to the current times the length of the wire times the strength of the magnetic field times the sine of the angle between the current and the magnetic field.
So this was the original formula, right? But right now we're talking about a current. Now let's assume that instead of a current, we're talking about a charge. So basically what we're going to do is substitute some things here with some expressions that we know to see if we can convert this formula. Instead of talking about a current, we're going to be talking about a charge. And actually the transformation there is very simple.
Field. Now, two of those variables don't apply to a single charge, the current I and the length L. But current is just equal.
Well, it's already there, but what can we substitute there? So we know that current is, well, that's actually a question in the next example. So what is current? How do we define current? Can somebody tell
Yes. I don't hear.
me? Yeah.
Current is equal to the voltage over the resistance.
Well, that's Ohm's law. That's it. No, but that's fine. That's a relationship between voltage and resistance, or voltage and current is given by resistance. That's Ohm law. That's correct. But current by itself, remember, current is the movement of charged particles. So current is a charge or the rate of movement of a charge. It's charge divided by time. So basically a current is coulombs per second. It's how fast a charge is moving. Okay. And so instead of current, we could talk about that.
To the number of charged particles passing a given point over a certain amount of time, which we'll call n, times their charge q, divided by that time t. For a single charge, n is just 1, and the length is just equal to velocity v multiplied by time. So we can apply these two facts to.
So basically, current is charge divided by time. It's basically, it's like a measure of velocity. It's charged by time. And in the case of a current, n is a lot of charges moving through a space. So let's assume that instead of being many charges, it's just one charge. So n equals 1. So current is charge divided by time. Is charge divided by time. Length is equal to velocity multiplied by time, or this is from dynamics. Velocity is displacement divided by time, okay? Or distance divided by time. In this case, it's called L, or it's the space that the charge is moving. So if we substitute those two in the original formula, actually time is going to be eliminated. And what we're going to be left with is that if I'm if I'm talking about one charged particle rather than a current, if I'm talking about just one charged particle, then the force that's going to be exerted on that charged particle is going to be directly proportional to the charge and the velocity the charge is moving through the magnetic field.
To our equation for force, which tells us that the force.
Why do we change? Why do we change the formulas? Because we're using the charge.
Yes, in the previous one, we were analyzing a current, so it's a bunch of charge that are moving through here. And as I mentioned, if there's a magnetic field, there's going to be a force on the whole cable. Now let's imagine that it isn't a lot of charges. We're just, you've got a gun, a pellet gun, and you're just shooting one charge. Just one charge. Which is actually what mentioned that's happening with the sun. The sun is kind of shooting a lot of charged particles to the earth, and those are being repelled by a force. So in this situation, we're just talking about a single charge.
On an electric.
Yes.
I have another question, sorry.
Go ahead.
Why do we substitute the length for velocity change cycle?
That's just because if it's one charged particle, we're really not interested how far it went. we're interested in its speed.
Okay.
So again, imagine the river that's flowing and you throw the rock. If you throw the rock like without much force, then it's gonna just bounce a little. But if you throw it harder, it's gonna not react as much to the river. So right now, the velocity is gonna be something important because how fast or how slow it's going through the magnetic field is gonna be is going to be a factor with regards to the force.
Charge moving through a magnetic field is equal to Q divided by time, multiplied by velocity times time, times the strength of the magnetic field, times the sine of theta. These two t's cancel each other out, so the equation simplifies to F equals QVB sine theta. That means that like the force on a current running through a wire, the force on a single electric charge depends on 4 factors. One is the same as with a current. The stronger the magnetic field, the stronger the force. The other 3 factors are slightly different from the case with a current. First, the force is stronger the closer to perpendicular the charge's velocity is to the magnetic field lines, which means that if the charge's velocity is parallel to the magnetic field lines, there won't be any force on it whatsoever. Second, the more charge the particle has, the stronger the force. And third, the faster the particle is moving, the stronger the force. Finding the direction of this force is where the third right-hand rule comes in. So get your right hand out again, straighten your fingers with your thumb stretched outward, then point your arm in the direction of the particle's velocity. Then bend your fingers to make them point in the direction of the magnetic field lines. This is where things get a little tricky. If the charged particle is positive, your thumb is pointing in the direction of the force. But if it's negative, the force is pointing in the direction opposite.
Okay, so this is the variation of the right hand. In the second right hand rule, we had a wire, and always the arm is going to be in the direction of the movement of the current. The fingers are always going to be in the direction of the magnetic field, and the thumb is always going to be the force. The difference here is that instead of talking about a current, we're talking about just one particle, or one charged particle. But remember that charged particles can be positive or negative, right? So it's going to be the same thing. Your arm is indicating the direction of the particle, where the particle is moving. Okay? The fingers are going to indicate the direction of the magnetic field. And your thumb is going to indicate the force. Okay, this is where nature kind of tried to do a weird joke, because if the particle is positive, then your finger or your thumb is pointing in the direction of the force. But if it's negative, you basically need to break your thumb and point it to the other side because it's opposing. Okay, so instead of using, oh no, if it's negative, I'm going to use the other hand, it doesn't work. It still has to be the right hand rule. So if the charge is positive, the thumb is pointing towards the force. If the charge is negative, the only thing it means is that it's going to the other side, but you can't like break your thumb. Well, that could be one way. Yeah, actually, that could be one way of doing it. Instead of pointing at that, if it's negative, you just. That was really drastic. I didn't have to break it this way. You could do it this way. So instead of doing this, you just do this, and it's going to the other side. If it's negative, yeah, that's right. Look for simpler solutions that don't imply bodily harm. That's good, Estrella. I was thinking about twisting. It was probably the Doctor Strange movie.
Your thumb. So electric currents create magnetic fields, and magnetic fields exert forces on electric currents and charges. Ørsted's experiment was simple, but his discovery linked 2 major fields of physics and inspired other scientists to do a lot more experimenting. Today you learned about magnetism and the magnetic field created by a current running through a wire. We also talked about the force from a magnetic field on a current running through a wire and on a single charge moving through a magnetic field. And we went through the 3 right-hand rules. Thanks to Prudential for sponsoring this episode. Saving a little more.
Okay, so let's see if we can apply this and see if we can visualize it with some exercises. Oh, by the way, remember that you've got the PowerPoint saying and Blackboard. So the videos are here, and you can rewatch the video, this one in particular. But the summary of the video and the mathematical expressions are here in the PowerPoint. Here are the summary of the expressions and the 3 right-hand rules. They're in the PowerPoint as well. So let's see if we can try to apply these to a few problems. So we're going to have 6 situations there. I'm going to explain what the graphics there in the situation mean, and we're going to go through them and see if we can understand. Yes.
To the slide on the right.
This one?
Yes.
Yeah, go ahead. Yeah, I'm gonna leave that in a moment.
So the figure is always gonna be the magnetic field, right?
They're always gonna be the magnetic field, yes. Yes. In the first one?
No, the third one.
The third one? The thumb is gonna be the force.
Thank you.
Force. Okay, so I'm gonna move on. Okay. So, the exercises that we're gonna practice right now have to do with the right-hand rule. And basically the expression that we saw, which is basically the last one, this one, that has to do with a charge that's moving through a magnetic field, okay? Let me explain what the diagrams mean, or what the symbology on the diagram there is. First off, the green lines are going to be the magnetic field. The green, and they have an arrow that's indicating where it's going. Now, in some cases, the magnetic field is going to be going into or out of the page, or what we're seeing in 3D dimensions. If we see an X, it's like an arrow. The X is meaning that I'm seeing the magnetic field from behind. So an X means that it's going inwards. A dot means that I'm looking at the arrow face on. It means it's going outwards.
Okay.
Okay. That's
what it means. No nos cae bien.
X means it's going inwards. The dot or the point means it's going outwards or towards me. The red arrow is going to indicate the movement of the particle. Okay, so it means the particle is moving in that direction. It's been shot. Imagine it's being shot through the magnetic field, and it's going or moving in that direction.
I'm going to find the force.
And what we do, what we want to do is we want to find the force that's being exerted in each of these situations.
Where are the areas?
Where are the what?
The cross field.
This one, for example, the third example we have.
Okay.
So each example is different. In each case, the magnetic field is going in a different direction. So whenever we see an X, it means that the magnetic field is going inside. If we see a dot, it means the magnetic field is going out. And in each case, they're telling us if the charge is positive or negative. Okay. Remember that depending on if the charge is positive or negative is in the end where the force is going to be directed towards.
Here, for example, in the first one, the magnetic field would be like this.
The first one, let's look at the first one. Let's start with the first one. Let's look at the first one. Remember, there's three things that we're looking at: the magnetic field, the direction of the movement of the charge, which is given, which is the vector of the velocity, and the force. The direction of the movement of the charge, that's your arm. The magnetic field are your fingers, and your thumb is the force. And what we're looking for is the force. Okay. So in the first case, and you can do that there in your practice, and I mean you can practice it there. The particle is going upwards. Okay, going upwards. It's positive. The particle is going upwards. I'm pointing it toward like the arrow. Okay. And the magnetic field is going this way. Okay. And so where is my thumb pointing? Towards the board. That means that the force is going
Inside.
into the particle is trying to go like this. It's trying to go inside. The force is pushing it into the board in this case. Was it clear how we applied the rule?
Yes.
Try to, I'm gonna do it again. Try to visualize. First, right hand rule again. Your arm is pointing in the direction of the particle. That's the way it's moving. And then the electrical field, that's the B. Those are those arrows.
Okay.
The electrical field are these arrows here. Okay. And so where is my finger pointing? Pointing inside. Okay. You see that? Oh, I'm doing it here in the
Yes,
whiteboard.
what's not inwards?
Excuse me?
Yes, what's not inwards?
No, but that's-
There's no-
Yes.
There's no X. Ah, okay.
What we're gonna do in the diagram is that since it's inwards, we're gonna indicate the force with an X because it's inwards. Okay. We're gonna indicate it with an X. This little dot here, this is just the charge. This doesn't represent either a dot or an X. Okay. Is it clear how we did it? Yes. One thing I'm gonna let you guys do in the next exercise for you to copy it in your page, so you can do the right hand rule in your page and not here in the board because it might be different. And so I literally took pictures of my hand. That's my hand, but that's not from a website or anything like that. That's my hand. I took pictures of my hand to do these exercises. So that's basically what we're.
How do you know that let's just calculate that force? You're substituting the values of the.
Oh, yeah, we're gonna get that to that in a moment, but yes, the calculation of the force is just simply substituting the values, and I'm gonna write that down here. Before we do that, is it clear how we calculated that? So the X represents the thumb. The thumb is going inside, so the force is going that way. It's going inside the page. Okay. So inside the page, you can remember that they're telling us that the charge is positive. So the force is going to go in the direction of where my thumb is going. Now, what magnitude is that force going to have? Well,
And the fingers are is the electric field.
it's the electric field.
No, isn't it the magnet?
Magnetic field. Magnetic field. Yeah. And so
Sir, what was the fourth formula?
I'm gonna write that down here. So force for a charged particle is gonna be Q, which is the charge, multiplied by the velocity, multiplied by the magnetic field, multiplied by the sine of the angle between the moving particle and the magnetic field. So in this case, we have all of the variables. So force is going to be equal to the charge is 5 microcoulombs. So it's going to be 5
What
times,
does that V mean?
which B? The V is velocity, the B is magnetic field. The charge is moving at 15 times 10 to the 3 meters per second. The B is, or the magnetic field is 0.25 Teslas. And the angle is 65 degrees. So it's going to be sine of 65 degrees.
Professor, that formula is different from the one before, right?
No, it's the last formula we saw. So the second one we saw was current. Yes.
In B, it's only 0.25.
Yes, it doesn't have a multiplier in this case. The values of the magnetic fields are in Teslas, and they should be smaller than 1. As was mentioned in the video, 1 Tesla magnetic field is a very large one.
There's a formula for charged particles.
Excuse me?
There's a formula for the
Charged particles, yes.
Well, it's for an individual charged particle, right?
Yeah, an individual charge particle, correct.
The other formula only changes in N, right?
Yeah, that's because the other formula, if we're talking about a current, that's because it's many charged particles, and it's just going to be 1 here. And if we calculate that, we should get this the value that's here. Remember to have your calculators in degrees. Yeah. Remember to verify the multipliers as well. The times 10 to the 3 and the times 10 to the minus 6. Okay. You're getting the value, but with a different one. Did you guys get the value? Get the value? Or get it? You did get the value? Just check the multipliers and the times 10 to the 3 and how you're putting them. Okay.
I got 1.
You also got to the minus 8?
Yes.
I got 1.7 times 10 to 8.
Yeah, just check the multipliers for your putting them in the formula and how you're putting them in what.
What's the answer?
Okay, questions with this one before we jump over to the next one?
Ah, eso es nomás a la. No, yo no tres. Oops. You put negative, that's not good.
Okay. I'm gonna jump to the next one.
¿Alguien tiene un cargador?
Okay, okay, now I'm gonna give you a minute to look at this one and see how this one would go. Before we, first again, try to use the rule, maybe write it down in your, and try to visualize, first off, in what direction.
It's also going inwards, no?
But also look at the charges. But the charges, remember to look at the values of the charges.
No, parece que estoy dándole creo que no manches. Es negro. Sí.
Ah, okay.
Entonces, so it's towards us.
Entonces, así.
So let's look at this one. So first off, the charge, the movement of the charge is pointed by the arrow. In this case, the magnetic field is going downwards. Those are the fingers. And that would mean that for this situation, my thumb is going into the wall. However, the charge is negative. So using Estrella's modification of the right-hand rule, instead of the force going into the screen, because it's negative, it's going to be going outwards. Okay, so in this case, it will be going out of the screen. The calculation is exactly the same as the other one with the same magnitudes. So in this case, no, that's a good question. No, when we do calculate similar to Coulomb's law, we just use the magnitudes. The direction is being given by the right-hand rule. So again, force is going to be equal to Q V B sine of theta. So remember, and Alejandra made a very good question right now. When we're applying the formulas, we don't put the signs of the charges in the formulas, okay? Similar to when we were working with electrical fields.
She gave me minus 3.81 times 10.
Mhm.
But it's not negative.
No, remember, we don't put the,
Ah, that's fine.
yeah, we're just calculating the magnitude. The magnitude is going to be an absolute value. The direction is being given by what the right-hand rule is telling us.
Because there's nothing in it.
No, we're calculating the magnitude, so we don't, similar to Coulomb's law, we don't substitute the signs in the expression because the expression only calculates the magnitude. The direction is being given by the right hand. Okay, let's do one more. Okay, let's do that one then.
Tenemos un amigo que está en esta
Actually, for that one, they're already giving a spoiler. They're already giving us the direction of the force. Oh, so the X's mean, in the case of, the X's are gonna mean that it's going inward. So the magnetic field is pointing inside it's going away from it. Actually, they're already giving us the direction of the force in that. In this case, the velocity or the charge is moving that way. The magnetic field is moving inside the screen. And that means that our thumb is going to be pointing upwards where this line is here. So the force is going to be pointing that way. Remember that the force and the are always going to be perpendicular. The angle is going to be given between the field and the yes. No, the angle is kind of hidden here. It's 60 degrees. It's hidden here. Hidden between the yes. Oh, the angle is gonna, so in the previous one, the angle is always gonna be the angle between the magnetic field lines and the velocity. So you're always gonna go from the velocity to the magnetic field.
I know. Oh, so that's why they give us a magnetic field because that's confusing.
Mhm. Magnetic field is pointing inward, so the angle is given.
So instead of being like this or like this,
Excuse me?
instead of being like this, because the default is to be like this, right?
Uh-huh.
And so because they give us a magnetic field.
You kind of rotate.
Es the right hand.
Ya sí, yo me acordé. Ahorita que dijiste.
So the angle we're going to do like this.
Wait a minute.
But there you put here, angle is like.
No, actually, this is misleading. No, that's a good observation. This is misleading. Yeah. This 60 degrees. Yeah, this is misleading. This 60 degrees. The the force is completely perpendicular to the magnetic field. I know this is a typo, this 60 shouldn't be here. The magnetic field is perpendicular to the direction, so it's going directly into the wall, and it's going to be perpendicular to the velocity, so the angle will be 90 degrees. This 60 degrees, so I'm gonna mark this. So this 60 degrees, we don't need this. Yeah, it's between the angle between the velocity and the magnetic field. No, that's a typo here. It's not, the velocity is going this way. So the particle is going this way, and the magnetic field is going directly into the wall, so the angle that's being formed is 90 degrees. That was misleading. I don't know why they wrote that down there. So if we do the calculation, F equals QV B, we should get the 1.875. So here, F equals QVB sine of theta. F equals Q, which is 5 times 10 to the minus 6. V is 15 times 10 to the 3. B is 0.25 and the sine of 90 degrees. And that should give us, this should give us this one here. Yes.
This would be like, because the force.
The heel is going this way, so your thumb is going.
Professor,
Yes.
when are these, what is the?
The Return of the Jedi one, that was for today. The essay for the Return of the Jedi. The other one, I think I left. Yeah, yeah. The Prestige one, I think they left that for the 27th or something like that. We've got enough time to do that. That's more for the fans, really. That one, if you want to do it.
But if I make like a job, can I have a point?
No, that has to be well done. I am a fan, so I know if you've seen it or not.
I am not a sci-fi fan. You do it.
Because I used to be a Star Wars diehard fan, but I'm not now. So I don't.
Yeah, it's again, that's for the more of the hardcore fans there.
I used to be very hardcore.
Hasta Marvel se me hace muy sci-fi para mí. Se me hace mucha pelea innecesaria, mucha historia innecesaria. Jamás he visto la película. ¿Qué?